presentation is titled Number Theory Neat Examples, Set 1. My name is Anton Antonov. Today is January 26, 2025. In this presentation, we are going to look into neat examples with primes and different arrangements of and plots of primes. So what are neat examples? These are concise and straightforward code what produces compelling visual textual outputs. We're showcasing certain programming language, Raku in this case, and the Raku modules, math number theory and JavaScript D3. Math number theory is for the number theory computations, and the visualizations are provided by JavaScript D3. This is a Visual Studio Code integrated development environment. I'm using the Jupyter framework. This Raku chatbook is based on Jupyter. And Jupyter is a web browser technology, hence JavaScript code can be rendered in it and produce visualizations by generating JavaScript code. Now, the first example of this is very probably not very compelling, but actually, let's see this here. So we have this table of numbers, and I have highlighted the prime numbers, and we can actually see with the function prime pi how many prime numbers we have, up to 25. So prime pi gives us the number of primes equal or smaller than the argument. Now, in order to make this neater, we're going to use a larger number here. And so, yeah, it's pretty straightforward, table with highlighted primes. What is so neat about it? Well, these functions to HTML table highlight, they come with a package called data translators, which is automatically loaded if you use Raku chatbook. And Raku chatbook has this magic cell for HTML code. So if the result is HTML, it's being automatically rendered in this way. Now, is prime which is being used, you can see it here, right? Is prime is being used to do the highlights. Is prime is being extended in this math number theory package to work with Gaussian integers. Gaussian integers are complex numbers in which both the real and the imaginary part are integer. And so here I have highlighted the real primes, which are actually Gaussian primes. So not all primes Gaussian primes. So you can see it here. First, actually, let me evaluate this. So you can see, like, say 13. 13 is a sum of two squares, and hence it can be represented in this way. These two complex numbers being multiplied. So 13 is not a Gaussian prime, and there's several theorems related to that, and we can see that in order to have a real prime to be a Gaussian prime, the remainder by dividing by 4 should be 3. And so basically this is verified here. All right, so in the early 30s, last century, the herpetologist Lawrence Kluber produced this geometric arrangement using a triangle, and pretty neat. And so we can see some kind of diagonals emerging with the primes. Is this holding? Well, it's an interesting question. So here this is a larger triangle, right? And so we can see we have some kind of pretty dense lines, straight lines, vertical lines with prime numbers. The one we saw here, right? It's actually somewhere here. All right, so this can be used to produce this type of neat examples in which I'm just splicing together two of these Kluber triangles, and I'm randomly using some kind of color scheme to color the result. If you want to see what this looks like, maybe this is neater. Somebody might find this to be neater than using the larger number triangles. All right, so Kluber triangle is very similar in spirit by the so-called Ulam spiral. Ulam spiral was invented by the Polish mathematician Stanislav Ulam in the early 60s. It was popularized by Martin Gardner and his column in Scientific American. I was reading the Russian translation of Scientific American as a teenager. I grew up reading Martin Gardner's books called Mathematical Recreations, or Mathematical Games, translated to Bulgarian. also to Russian, of course. So anyway, so here is the Ulam spiral. So you see we start in the center and then we kind of go like this, and then we mark the primes. So spiral lattice is provided by math number theory utilities that, and I can actually specify where I want the spiral to finish. If I say top right, for example, right? I mean, this can it can finish here, but yeah, let's return it. This is the bottom, the spiral finishing in the bottom right. That's the normal way the spiral is being plotted. All right, so let's actually just plot the primes, not the marking, but just the primes, which is actually how the Ulam spiral is supposed to look like, and then we can make the corresponding plots. And so this actually, again, I'm actually using the prime number, the actual prime numbers values as to color the results, but the Ulam spiral is supposed to look like this, right? Supposed to be with this mono color, and so I'm going to return it again because it's visually more compelling to look into this. And yeah, if you look more closely to the center, you start to see more details. All right, so there's something called prime generating polynomials, and so this here actually we can show that this polynomial generates a bunch of prime numbers which actually line up in this diagonal. All of the diagonals are described by polynomials like this, this a, b, c, the coefficients need to be different, but yeah, this was one of the compelling features of the Ulam spiral. I'm going to be using the Ulam spiral a lot to do the neat examples for the next sets, right? So okay, here next prime, it's a functions like I'm actually, so next prime, if I have certain numbers, say 14, next prime gives me the prime after 14, right? But I can actually also get the second next prime and so forth, right? And so I mean, if I what was initially here, if I put 20, yeah, we can get you can go up further, and so we can get the 20th prime after 14. So these functions, is prime, next prime, prime pi, they're all related, and so here let's actually do a few tabulations like this. So instead of using is prime, I'm basically, if not pretending, I'm basically showing what is the relationship here. So here I have generated these numbers, from 1 to 70. I have these numbers, and I make the following check. If the number is equal to the next prime of the number before it, right? Next prime applied to the number before it. Well, then this number is prime, right? So this is what is happening here. We can visualize the sieve of Eratosthenes using next prime. That's actually very neat examples. All of these neat examples, probably majority of them, maybe 60 to 70%, have been inspired from the neat examples in the Wolfram language functions, number theory functions. And many of the number theory functions were, again, design and functionalities taken from or duplicate what is in Wolfram language, but I have refitted them to Raku, to the Raku idiomatic application and naming conventions. So here the sieve of Eratosthenes, again, neat example, but this is not exactly how the sieve of Eratosthenes works. But in some sense, we're using next prime to filter out, to make this iterative elements of the sieve of Eratosthenes. So if you're not familiar, this is sieve of Eratosthenes is probably one of the oldest algorithms which is still used nowadays. It was from ancient Greece, and we iteratively, from a given set of numbers, we iteratively remove numbers we know are being divided by a certain number. We start from 1, or start from 2, and then we remove everything which is divided by 2, then remove everything which is divided by 3, and so forth. We accumulate the numbers, the smallest numbers which we obtain, and those are our primes. And more or less this is what is happening here. It's quite interesting to visualize those numbers in this way using sinusoids. All right, so my next example is with the Ulam spiral. This is one of the best looking Ulam spirals actually. So what is happening here is that I make the spiral lattice, and I color the point, color each number in the spiral. I color it according to the difference of the next prime applied to it and the number, right? So it's what getting produced. So we can also do the sunflower pattern spiral. So I'm going to explain what's going on here. Let me actually show the sunflower pattern. We saw it in the beginning. So yeah, basically look like this. And I have in this particular case, I have actually grouped the points with mod 4 because of what I was saying about Gaussian integers earlier. So what is going on here? So we take these numbers from 1 to 15,000 and we find the next prime. So next prime is basically partitioning those numbers into certain categories or classes, if you will. And I don't need to take unique of this. I can plot it. Basically, will be the corresponding points are going to be on top of each other, but we can save computations by calling unique. And so you can see here I'm using the actual number, the actual prime in this case, to produce a certain angle, and I'm also using this number to for the radius or whatever, for the length of the norm of which this number is being plotted. This is kind of a standard way of making the sunflower patterns. This phi is provided by the package. This is the golden ratio, and say 360 degrees divided by phi square is the golden angle. Here it's in radians, and so the golden angle is like this, like 137 degrees. Very interesting to know how sunflowers actually manifest this golden angle, and this article here discusses that. This has been known for quite a while about the spirals, the Fibonacci, the numbers of Fibonacci being found in the sunflowers, but the actual explanations why is this happening involves say not just mathematics but also physics and biochemistry, and this was relatively recent how the explanations, the full explanation was being done. So here in this, let me actually show with the legends, show the legend. And so you can see here 2 is kind of lurking, right? So because I'm using mod 4, I'm looking into the reminders of dividing by 4. So you can see the ones in blue, these are the Gaussian primes, right? And the rest are non-Gaussian primes. And 2 is the only one which with mod 4 it doesn't, it has this, it gives 2. Okay, so let me return to the original here. All right, let's actually expand a little bit on this pattern or make it somewhat prettier. And so I'm going to start the computation here. I'm going to explain what's going on. So we're going to use this function prime omega. Prime omega gives the number of prime factors with their multiplicities. So you can see here, like it's a relatively simple formula. If you have a certain integer being decomposed into this way, you basically sum the powers here. Okay, so here again I'm taking from 2 to 15,000, and actually this was redundant. Obviously I've been reusing the code above, and so I'm finding this prime omega and I'm looking at the inverse. That's why 1 is not here, right? Because it's going to be 0. So I'm actually trying to make these points, these points here, or disks. I'm using bubble chart here, so they're points, but actually they're disks. So I'm using bubble chart. So basically the ones which are the disks or the points which are the largest, these are the prime numbers, and the others, the size of the others depends on how much powers of other primes they have in their decomposition, basically this here. And so yeah, you can see we have this kind of nice pattern. I have looked into the breakdown of this of these values here for x and y, and I have selected them in such a way, like say from minus 100 to 100 for x and minus 70 to 70 for y, in order to have this rectangular kind of fill in, right? Okay, so this was it. Thank you for your attention.